SwayamPrabha. Digital India. Educated India.
Welcome back. In lecture 30, we will talk about water treatment, and this is the third part. The different concepts that we will cover in this lecture are on filtration, disinfection, other treatments, and then we will look into some case studies. So, the filtration, in this process, water is passed through beds of granular materials, which is the filter, and this actually could be of different kinds of filter materials could be utilized, but usually we have got a thick layer of sand, and this helps in removal of bacteria and other impurities, and particularly color, taste, and odor. These are removed as well. So, the process of filtration involves many steps, or rather it involves different ways of removal of these impurities. The first process is mechanical straining, that is the straining action of the pores in the sand. That means any kind of filter media, either sand or maybe some sort of pebbles or maybe some sort of gravel or coarse sand, these have got pores in that, and the straining action of the pores help in retaining the impurities. So, that means they are stuck, the impurities bigger than those particular pores cannot pass through. Pore sizes are reduced due to adherence of suspended particles. So, the more amount of filtration happens, the pore size gradually get clogged, and arrested particles including the coagulated floc forms a mat on the surface, which further helps in straining. So, that means the pore sizes even get smaller because this arrested particles or the coagulated floc, they form a film on the surface of the sand, and this also helps in further straining, right. Then, along with mechanical straining, we also have natural flocculation and sedimentation. How it happens? Within the void spaces of this particular, in this particular sand, as these voids are basically act as tiny coagulation sedimentation tanks. So, particles and bacteria which are even smaller than the pores, which can pass through the pores, but they come to this particular sedimentation tanks, and usually they are acted upon by because they form this gelatinous mass, this further attaches to the incoming fine particles. So, they are able to retain other particles which are even smaller in size and are able to pass through the pores. So, because we are creating this sort of coagulant sedimentation tanks inside these pores in the soil itself. Then biological action happens, and as you understand that this coagulant sedimentation, this tanks or this area, this has this particular film, and suspended organic impurities are acted upon by microorganisms which get trapped in the pores, or particularly on the slime that we talked just earlier, including, and this microorganisms act on the organic impurities and they are able to break it down further. And when this and eventually this layer of this slime layer gradually becomes thicker and thicker, and finally the filtration efficiency also reduces. So, in addition to all this, we also have electrolytic action, which is sand grains and ionized matter in water carry opposite electric charges, which helps in attracting and also neutralizing each other. This alters the chemical composition of water to some extent. But when the charges are exhausted, that means all the sand grains have lost the charge, then we have to actually clean this sand bed, and again it will start back from the beginning. That means again it will have its charge, and it can again help in separating the impurities by using this electrolytic action. So, that means that change in chemical composition actually helps in treatment of the water. Maybe it makes it more, it was too basic, that means we can, pH could be actually modified using this kind of action. So, filtration actually is it helps in different ways of, it actually is not a single way of preventing impurities or to pass through. It is not just the mechanical straining part, it has lot of other properties, like it helps in flocculation, sedimentation and biological action. This actually is a process which happens together, and also electrolytic action. All this together helps in further reduction of impurities or further reduction of BOD and so on. So, how is filtration achieved? Usually we have got these sand filters, and we have sand beds, and where sand of uniform size and effective size of sand particles should be as per specification. So, usually the sand should be as uniform as possible, and we have certain size of sands that is required. So, depth and that specification has to be followed. It has to be effective size, that means most of the sand has to be of that particular size. So, that is called the effective size. Then depth of sand bed should be between 60 to 90 centimeter at least, and then sand beds has different graded sands in different layers. So, it could be a same size of sand, or it could be of different kinds of sand that we can also put in. And we have got different kinds of filters. We can have either slow sand filter or rapid gravity filters. It all depends on the size of sand and what kind of filter media that we use. So, in slow sand filters, the effective size of sand is 0.3 to 0.35 millimeter, and uniformity coefficient of 1.75. Now, what is uniformity coefficient? That is the ratio between sieve size that will pass 60% to the effective size of sand, which is basically 10%. That means effective size of sand is basically, it means that most of the sand is of a particular size. So, that means in around 90%, because 10% actually refers to 90% of the sand is of same size, right? And and the ratio between sieve size to that is something around the uniformity coefficient, which is around 1.75. So, anyway, so this to understand that the size of sand is more or less in slow sand filter is smaller. In rapid gravity filters, the effective size is actually larger, which is 0.35 to 0.5 mm, and the uniformity coefficient is 1.6. So, both together the size and the uniformity coefficient plays a role, but particularly for basic understanding, you can understand that the size of sand in rapid gravity filters is larger. That means it allows more, the pore sizes would be larger, and that will allow more water to pass faster. So, sand bed is usually supported on a gravel bed of 30 to 60 centimeter, which helps movement of filtered water to the under drain. So, as you can see, there is the under drainage pipeline. So, we have got this gravel which is supporting the sand. So, water passes via the sand, via the gravel into the under drainage system, and sometimes compressed air is used through vertical pipes for efficient functioning, and usually compressed air is used for cleaning the sand and all this for backwashing. I will discuss that, but sometimes air is also passed to increase the efficiency of or increase the movement of this water. And top layer of sand is scraped and replaced with clean sand when filter stops working. So, the top layer of whenever we see that the filter is not working, that means there is a top layer formed which is preventing entry of water, which has gone thick. So, we have to remove that the top layer of sand, we have to clean it and again put it back. So, this is the design of a slow sand filter. So, you can see this is the from sedimentation tank, water comes in. This is the first chamber from where the water goes into the main filter, and here we can see that the water goes down. At the top we have fine sand, then we can also have coarse sand, or it could be pebbles directly or gravels directly, and below that we have the under drainage system from where water is collected into this particular sump from where we can take it out, and water is actually coming from the top. So, over here you see the head of water is over here, and over here the head is below. So, a float is used to determine this head, and this is called the loss of head. and to maintain that loss of head we have to adjust the flow rates in this particular unit. So, because the water is passing through a slower speed and all, it may lead to loss of head. So, this is one issue which has to be taken care of in design of water treatment plants. But again, it's it depends on how you want to adjust flow rate and so on. So, it's not directly a concern when we just want to understand that what sort of technology we want to use or what area is required and so on. So, sand filters, the size, depth is around 2.5 to 4 meter, surface area is 100 to 2000 square meters. So, that gives you an idea about the space requirement. It removes bacterial load of around 99% and color 20 to 25%. This gives you an idea about what sort of quality you can achieve with this particular type of filter. Turbidity it can deal with is up to 50 ppm, and if beyond 50 ppm you have to go with other kinds of plain sedimentation, other processes. So, that also will help you to determine when you should directly use a filter instead of going for sedimentation and the coagulation and other processes. The flow rate is 100 to 200 liter per meter square. So, that actually gives you an idea about the the surface area that is required or the total size of tank that is required. Difference in water level in filter and outlet chamber is basically due to loss of head. Then we have rapid gravity filters. These are open watertight rectangular masonry or concrete tanks, and depth is 2.5 to 3.5 meter and surface area is 10 to 80 square meter each. So, you can see the size is much smaller compared to slow sand filters. So, because here everything has to be done faster. So, instead of having one unit, we have got multiple units, and parallelly water goes into all these units and then it is taken out. So, how many units are required? So, there is a simple formula where you can use 1.22 into root Q, where Q is quantity in million liters per day. Based on that, you can determine the number of units that is required for this rapid gravity filters. And in rapid gravity filters, we use gravel layers. Around 5 to 6 layers of 10 to 15 centimeter each is used. Sometimes rapid gravity filters could be also made of coarse sand and all, but it's better. Sometimes we have it for gravel layers of 5 to 6 layers, so that is also possible. And we have got a flow rate controller which maintains uniform flow, and compressed air is also used, and compressed air is particularly used to actually when we want to clean this particular filter when it is clogged, we pass compressed air, and that actually helps in loosening the pores of these particles and all. And then by backwashing, that means we send water in the opposite direction, and that actually cleans up the pores, and the water is collected in some troughs at the top. So, that means over here in this particular image you can see that there is a gangway at the top from where you can really open and control the valves. So, the first is the inlet channel over here, then this is the sand filter, then this is coarse sand, then there are pebbles. There could be different designs, it could be all different layers of gravel also, or different layers of sand. So, it depends on how you what kind of rate of treatment you want. Based on that you can decide on this kind of arrangement. And over here you can see the compressed air pipe through which when we blow air, the clogs are actually loosened up, and over here the water comes down and the water is taken out, and then this goes into this outlet, and the clean water goes into this outlet, and wastewater, and this is the wastewater channel. And what happens is we have got this water, and this sometimes this through this, as you can see that whenever we want to do backwashing, that means we have to also allow water back into the system. That means through this we can also allow water. We close this particular valve, we can use this water inlet, and through which water can be sent inside, and we can actually send water to go up. And when water goes upwards, it actually cleans during backwashing, of course, it cleans the pores, it goes in the opposite direction, it loosens, and using compressed air we have already loosened the pores, and then we send water, and then it cleans the pores, the water goes up, and then we can open these valves, and the water can be collected into this pipe. We open this particular valve, and then water taken out through this outlet and then let out. So, this is the wastewater, this is how it could be taken out. and the clean water could be taken out even from below in another direction as well. So, when the filter is working. So, wash water troughs for backwashing 1.5 to 2.5 meter. Usually, this kind of troughs are at the top, so that when the dirty water comes up, it is collected in those troughs and it could be taken out. And also, this is another arrangement where we have a pipe through which the water could be also taken out. So, removes bacterial load partially. Because, compared to a slow sand filter, the process is much faster, and obviously the treatment level is lesser. So, it removes bacterial load partially, turbidity up to 35 to 40 ppm, and flow rate is 3000 to 6000 liter per meter square. So, you can see the flow rate is much higher than the slow sand filter. So, that is the difference between a slow sand filter and a rapid gravity filter. Then we take the pressure filter. So, this is another form of rapid gravity filter, you can say, but here it is basically a rapid sand filter, but it is in a watertight closed steel cylinder, and it is a totally compact process where coagulated water directly put in, and water without mixing and flocculation, and water pressure is higher than atmosphere. We create pressure by putting the water at a higher pressure. And this is automatic operation, relatively expensive, and we use compact chambers. So, it is compact dimensions, and efficiency in removing bacteria and turbidity is lower compared to the other filters, but flow rate is much higher, like 6000 to 15,000 liters per meter square per hour. So, in over here water was applied and we were depending on gravity for the water to come down. Over here water is applied at a pressure, and it is a pressurized chamber. So, water cannot go out. So, it will come down. So, it is pressured through the sand layers and then it is taken out. So, the treatment level is lower, but the flow rate could be much higher. Then this is backwashing. This is washing of filters. So, for that we have got a overhead tank. So, this is the wash water tank, and this is the filtered water this is our sand filter. So, we use compressed air for cleaning the pores and all that we have discussed. So, this is inlet. So, water comes in, it gradually cleaned through via the filter, and then it is collected over here. Some amount of water is taken to the service reservoir, but some amount of water is pumped to the overhead wash water tank. And when we need to clean it, we stop the operation by using valves. Instead, we release the water over here, the water flows over here, and then it goes up, and then it is collected in, it cleans the filter, and then it gets collected in troughs. So, backwashing or backflow of water through sand bed, inlet is closed and most of the water is drained. This is the first step. Then compressed air is passed for 2 to 3 minutes to loosen the dirt. Then water from wash water tank is allowed to backflow. Sand expands and all dirt is carried away. Washing done every 24 hours and lasts for 10 minutes. So, every day we do have to do washing in case of sand filters. Otherwise, it will not work. And wash water troughs above the filter media collect backwash water and carry it to the drain. So, that is another in this ones. In the previous design, we have used another set of pipelines to carry that, but we can also have troughs which are channels which we can also construct through which this this wash water could be taken out. So, this is the image of a rapid gravity filter that you can see over here. So, this is other sections. So, over here you can see the wash water troughs that is indicated over. These are the wash water troughs. So, water comes up and then it could be carried out through these troughs, and this is the overall tank, and influent goes in from these pipelines, pressure lines to hydraulic valves from operating tables, and then effluent comes out from below over here. This is the wash line, then these are other drainage channels and so on. So, this actually shows you the kind of layers. That means, this is the graded gravel. This is the lower part from where there is this cast iron manifold with strainers in the tops to allow entry of water, and this are the perforated laterals through which water is taken out from below. And this is the wash troughs at the top, and this is the filter sand. So, this is more or less a section of this rapid gravity filter. So, the next process is disinfection. In this process, we try to kill the pathogens in water using chemicals, or sometimes other substances or processes are also used. So, it is not only just mixing chemicals, we can use some other processes as well, and it should be effective within the required time and temperature. So, that means the process should be effective at that particular temperature and for a particular time period. That means once we do that, it should remain the pathogens should not be there in water for a certain amount of time when the water stays in the distribution network and so on till the time it is consumed. And after treatment, water should not be toxic or objectionable. That means the use of the chemical should not make it objectionable. Residual concentration should be ensured to protect against contamination during storage and transmission. So, that means we would try to give a little bit extra chemical or whatever way we are doing disinfection, so that even after the time period it is treated till the time it is consumed, it still remains safe. So, there are different processes of disinfection. The first process is boiling of water. Boiling for 15 to 20 minutes obviously removes all pathogens, but as you know, this is costly and this is not suitable for public works. For home, in certain homes, for certain purposes we can use it, but for public works it doesn't is suitable because it is costly. You have to spend a lot of energy boiling water, and it doesn't offer any protection for future. That means during storage and transmission. We can use ultraviolet rays. This is again costly. Usually we use it in swimming pools because we don't want to use chemicals in swimming pools. But UV rays can reach up to 10 centimeter deep in water. And it is usually provided through mercury vapor in quartz lamp. So, we use quartz lamp with mercury vapor to create this UV rays. We can also use iodine and bromine. This kills all the bacteria, and maximum concentration could be given is 8 ppm. Time taken is around 5 minutes, and it is also available in pill form. Then we can also use ozone. Ozone means you can use nascent oxygen, which kills all pathogen, oxidizes all organic matter. We give a dosage of 2 to 3 ppm, residual is 0.1 ppm after 30 minutes, and ozone gas released in sterilizing chamber, and water is taken through this chamber, which removes color, odor and taste of water. So, this use of nascent oxygen, use of iodine, these are all processes which are used in different cases. Excess lime we can also use while we use lime for removal of hardness, that we have learnt earlier, but we can give excess lime that will result in killing of bacteria, and it raises the pH to 9.5, and because it raises the pH, it is usually not used. Potassium permanganate is a solution for rural areas. In villages for dug wells, ponds, we can use potassium permanganate, and this kills bacteria up till 98% and oxidizes organic matter. Dosage is around 1 to 2 milligram per liter for 4 to 6 hours. So, these are the different processes, but the most common process that we use is chlorination. This is both cheap, this is reliable, this is easy to handle and provide residual disinfection effects for long periods. So, this is one of the primary reasons why we use chlorine, and it is used, chlorine in various forms are used, and but if there is too much of chlorine, it actually results in bad taste. Sometimes it leads to loss of hair even, and chlorine when added to water forms hypochlorous acid, which have hypochlorite ions, which affects most of the microorganisms. So, this is the likely process in which microorganisms get killed. And chlorine also reacts with ammonia in water and to form chloramines, which also removes odor and can have the property to disinfect. So, chlorine demand for water, that is the difference between added and remaining chlorine in water after a specified period. So, how much chlorine is required to be added in a water, or what is the chlorine demand for water? We add some amount of chlorine, and after a specified period we see how much of it is there still in water, and that means that so much amount of chlorine is actually utilized for disinfection. So, based on that we can determine the total amount of chlorine that is used. When it is not further reduced, then we can understand that no further chlorine is being utilized. So, chlorine consuming substances are inorganic, organic and ammonia, that actually takes up the chlorine, and this actually also depends on time of contact, pH of water, temperature and so on. So, based on that we determine what sort of chlorine, rate of chlorine application should be provided, but usually when we have certain kind of pandemics or certain other epidemics around, that means there is chance of more contamination. In that case, we add a little bit more chlorine than usual. So, this process is known as super chlorination, and we add 2 to 3 ppm beyond the breakpoint of chlorine. And sometimes dechlorination is also done to remove excess chlorine from water. Now, usually there is pre-chlorination and post-chlorination. So, if you remember from our earlier lectures, we have talked about pre-chlorination and post-chlorination. Post-chlorination is adding of chlorine after the process of filtration. So, after filtration we will add chlorine for disinfection. So, minimum contact period is 30 minutes before use. So, that is the way we do post-chlorination. And in case of pre-chlorination, chlorine added before sedimentation, but a small dose is added compared to post-chlorination, and this is adjusted so that at filtration unit concentration is around 0.1 to 0.5 ppm. And this is applied through bleaching powder. Chlorine is applied via bleaching powder, chloramine, chlorine dioxide, liquid chlorine, or even in gaseous chlorine. So, in a treatment unit, we usually go for gaseous chlorine, and it is available in commercial cylinders, as you can see in this particular image, and we use chlorinators. This is a panel through which we can control the flow. So, we use chlorinators, which regulates the flow of gas from chlorine container to water supply, and this mixes the gases properly with water, and long pipelines are usually avoided for this kind of process. So, usually this is the absorption tower, as you can see, and this is where the chlorine gets absorbed into the water. Water is supplied over here and the water is taken out from over here. So, that is the absorption tower through which the chlorine that is being sent from this chlorine gas cylinder into this particular chamber. So, this is how we mix chlorine in the water. So, some other treatments in addition to disinfection, these are in some water treatment plants, we depending on what type of water, we go for further treatment. For example, we can do water softening to reduce hardness. Temporary hardness could be removed by addition of lime, by boiling also, but boiling is usually not done, and permanent hardness could be removed through lime soda process or base exchange process or demineralization process. So, these are the different techniques that are utilized. Fluoridation, as we have discussed in earlier lectures, that both absence of fluoride causes cavities, whereas excess causes spotting, which is harmful. So, fluoride is added if less than 1 milligram per liter. So, that is when we have to also add fluoride. Then activated carbon, these are used to remove taste and odor in public water works, and these are used in powdered form before and after coagulation with sedimentation, and can be used in granular form in place of sand in rapid gravity filters. So, that is what I told you earlier. And then we have got distillation process. This is the best method for treating salt water, and steam is used to heat salt water so that it evaporates, and metal evaporators lined with Teflon is used to prevent crustation. So, that means once it evaporates, then again it is distillation, then again it becomes into liquid form and we get cleaner water, and for that we use metal evaporators lined with Teflon. So, next we study look into two case studies. One is the case study of Pune Municipal Corporation. So, in this treatment plant, what they have done is there is the inlet water comes. So, first they have protective bar screens, then there is a travelling water screen. So, they have got two sets of screens, then there is a low lift pump, then it is stored in a reservoir. From using low lift pump, it is then sent where pre-chlorination is done, and or you can say pre-oxidation is done, and then it is mixed with chemical coagulants, and then flocculation happens. Then we have a sedimentation basin, then we have got sand filtration. So, sedimentation basin is separate, this is not a clarificator, these are separate units. Then sand filtration is done. So, we have got different layers, and then post chlorination is done. In addition to that, fluoridation is done, and then there from the clean water chamber, then using high lift pumps, it is sent to the elevated water storage tower, from where it is sent to the different zones where water is supplied. So, usually we have both a they have used a micro strainer, they have used the process of aeration, then process of mixing, then pre-oxidation where application of oxidization agents like ozone, potassium permanganate, chlorine compounds, so sort of pre-chlorination you can say, then coagulation, flocculation, sedimentation, filtration and disinfection. So, these are the different treatment processes this Pune Municipal Corporation has adopted. Similarly, we study another case of water treatment plant. This is case study from Haroa, Rajarhat and Bhangat 2. This is in Kolkata area. So, this is where design, construction and operation of water treatment plant, reservoirs, transmission mains and pumping stations were all taken up together. So, this is a recent project and surface water based bulk water supply system. So, the water is from surface, the intake is at the surface water sources and then so this was done to reduce dependency on groundwater because the groundwater was arsenic contaminated, and this was done in the eastern side of the Kolkata city because some of these blocks were contaminated because of arsenic. Right. So, it was planned to bring the surface water from far away and then treat it over there and then supply. So, the raw surface water intake was river Hooghly at Rani Devendra Bala Ghat. So, you have seen the plan of Kolkata earlier. We have river Hooghly on one side and then we have got the city of Kolkata over like this, and then we have got Salt Lake over here, then this is New Town over at this side, right. So, this entire thing was somewhere around these zones, right, the entire New Town zone and so on. So, this project involved also developing the transmission main, that is from river Hooghly directly to this New Town, where the distance was 11.5 kilometers and the pipe diameter was around 1829 millimeter pipes were used, and raw water storage was first in 5 pre-settlement ponds. So, this is where pre-sedimentation happens, plain sedimentation happens. So, 5 pre-settlement ponds were also there in the water treatment plant. So, from there raw water intake sump to water treatment plant. So, the water is taken inside the water treatment plant, and the WTP they were planned, it was planned for 5 modules in 5 different phases. Already a 20 mgd or 91 million liters per day phase was done and it was operational since 2016. The next plan was to do a 22 mgd or 100 million liters, this million gallons per day or 22 million gallons per day, which is equivalent to 100 million liters per day. So, water treatment plant including raw water intake facility from this pre-settlement tank, of course, from the raw water ponds, or you can say that this is the pre-settlement ponds. So, clean water pumping main from WTP to booster pumping station. So, once the treatment was there, there was pumping main to the booster pumping stations. Far away at 4.3 kilometers with 1200 pipes, MS pipes were used. 600 kiloliter clear water reservoir and a booster pumping station was also constructed. Ground level service reservoirs of 3200 kiloliter and 5000 kiloliter were also constructed at Haroa and Bhangat 2. So, there were actually 3 clear water reservoirs which have been constructed. So, the entire contract including design, construction, supply and installation of equipment, commissioning and operation for 2 years was given to the agency. So, it is built, operate and then it is supposed to be transferred. So, it is a BOT contract. So, care was taken that surges in the pumps and also in the water treatment units was suppressed, or there was control mechanisms for surge suppression, and also overall system control was there. That means SCADA equipment was also installed in this particular system. So, this is the map where Newtown, this is the Newtown water treatment plant area. You can see these are the pre-settlement ponds. So, you can understand the size required compared to the size of the plant. So, this is that plant, right. So, this is, and these are the reserved areas. right, lot of reserved area. So, this is the details of that plant. You can see the different units over here, and from outside it looks like this. So, this is the building, and then inside you can see this is that that is the pump. This is the water treatment plant, and this is the sequence of the flowchart for water treatment plant. I will come back to that. So, the total project cost was around 686.95 crores. Total population served is around 5.26. This will give you an idea about the amount of money you required for this kind of project. So that you understand that whenever in a development, preparing a development plan, you make sure that this is the amount of finances that are available with the municipality. You can determine that what sort of plants you can actually put in, how many of those you can put in, at what phasing you need to do for that, and so on. So, the funding partly funded by the Asian Development Bank, and it was funded most by the Asian Development Bank and was executed by the state PhD department. And these are the different images you can see. These are the controls, these are valves, there are some equipment, these are semi-automatic control systems, right. So, what is the treatment sequence we have first pre-chlorination, then the intake sump and pump house. This is from the raw water is taken from that particular pre-sedimentation tank. We have an intake sump and a pump house from where water is taken. So, in the inlet chamber we are doing pre-chlorination, then we have inlet channel, then we have a partial flume. Partial flume is basically a fixed hydraulic structure used to measure volumetric flow rate. So, usually it looks like that. So, this is how the water flows and it is measured. And then we have got a distribution box, then we have a flash mixture. You know what's the flash mixture is for? It's for mixing the chemicals. And then we have a flocculation tank, then we have a plate settler, and from there we have got this is a settlement tank, that is a sedimentation tank. So, we have a sludge collection unit where there is a sludge pump. Then there is a rapid gravity filter which has got a backwash reservoir. And then from the sludge is actually taken to a sump where there is a recirculation pump to the inlet chamber. So, you see that sludge is recirculated back into the system. So, this is to some extent this actually sometimes so we have a solid semi sludge formed in the centrifuge room where the sludge is probably rotated. That means some amount of dewatering is taking place over here. And then we have got substations for electricity, administrative building. Then we have got a separate disinfection unit where the clean water from rapid gravity filter comes from filter house, and then we have that sump and clean water reservoir, pump house, and then it's sent to the boosting station. So, this you can see this sequence of events over there, and this all needs to be arranged. So, it's very difficult to say until unless the actual design is done. It's very difficult to say what amount of area is required for a particular pump house, for a particular water treatment unit, and so on. But roughly we can form an idea, and from that we can determine how much area is to be reserved for this kind of units. So, to conclude, the choice of slow sand or rapid gravity or pressure filter depends on quantity of water to be treated and level of treatment. Chlorine is most commonly used disinfectant, and the capital investment and area required for water treatment plant depends on its setup and treatment technology adopted, and area should be reserved for future expansion. So, this is the references that you can use. Thank you.